Hey everybody, this is Professor Mankowski, and in this video we're going to do an introduction to Chapter 8, which is all about hypothesis testing. And we're going to go ahead and start with an introductory example right away. Imagine that we're working on campus, and you have a job, and you're going to be delivering orientation for new incoming students. And before the orientation, our boss gives us this sheet of paper that has all these different things on it that we're supposed to be saying, and among those is a statistic. And it says that BCC students work an average of 5 hours a week. When you see the number 5, you're a little suspicious and you think that number should be a lot higher. And obviously, when you report the information during the orientation, you want to get the right number. So you decide that what you're going to do is take a quick sample of 100 students. And you're going to find out what's the average hours worked per week and find out if that average hours worked per week is a lot higher than the 5. So we're going to lay out what would be the distribution of hours worked per week, assuming that it's a normal distribution. And when we begin to do the sample, we're actually going to give our boss the benefit of the doubt. And we're going to assume that the average really stands at 5 hours per week. Now, what's really important to keep in mind is that when we take our sample, we're expecting our sample average to be off the mark a little bit from the true average. Meaning we don't expect X bar to be exactly equal to mu because of something called sampling error. And sampling error means that the sample will never be a perfect representation of the population. So there should be a little bit of minuscule fluctuation between the two. So we go ahead, we cast our net, we get our first sample, and it turns out to be that the people in the sample are working on average 5.1 hours per week. When we compare those two numbers, we're thinking, obviously 5.1 is a larger number than 5, but it's not drastically different. It doesn't seem like it gives us a whole lot of evidence to go ahead and refute the population average of 5. The difference between those two, in fact, is so small that we just attribute it to sampling error. We know that the X bar won't exactly equal mu, so that's what we believe the difference is to. Now we go ahead, we do another sample. And this time, our sample average is 5.3 hours. And again, 5.3 is, of course, higher than 5, but not by a drastic amount. So we still believe that it looks like our difference is simply due to sampling error. We take another sample. And this time, our X bar is 10 hours. Now, 10 is a lot bigger than 5 compared to the last two cases, but even so, is that far enough away from 5 for us to come out and challenge our boss and say we think that 5 hours needs an update? A little hard to tell. So let's take just a really extreme example. And we end up, let's imagine the sample hours came out to be 100 hours per week. And this time there's a very substantial difference between X bar and mu. And we're thinking, if we went ahead and we did a random unbiased sample and we ended up with 100 hours a week, that's so drastically different from 5 hours that it must be the case that the difference is not attributed to sampling error any longer. And it's therefore the case that that initially reported population average is much higher than 5 hours and needs to be updated. Now, how do you know when you're far enough away from the mu with your X bar to come out and make the case against HO? That's exactly what we're going to learn in hypothesis testing. We're going to find out how to do analysis using bell curves and everything we know about distributions to make that judgment call. Before we start doing sampling, though, before we start looking deeper into how we can look inside the sample and see if there's enough evidence to go and challenge that initially reported population average, there's one thing that we always have to do first before we begin that kind of an experiment. And we have to state what our hypothesis is. And there's two specific kinds of hypothesis. The first is what we call a null hypothesis. And null hypothesis is abbreviated as HO. And what it says is that the difference between the sample statistic, which in our case would be X bar, and the population average is insignificant, and it's simply considered due to sampling error. So the difference is so trivial that it's not enough to refute what's originally reported as the population average. So if that's the null hypothesis, what's on the opposite side? That's going to be what we call the alternative hypothesis. And the alternative hypothesis is abbreviated as H1. And it says this time the difference between the sample statistic and the population average is so large that we can't just attribute it to sampling error anymore. And it's letting us know that the initially reported population average must be a lot higher than what everybody else thinks it is. So as we're thinking about the null hypothesis and the alternative hypothesis, a couple takeaways. First, HO and H1 cannot both be true at the same exact time. And usually, if we end up reporting information, we're going to report it in terms of HO at the end of an experiment. So if we've got enough evidence to show that HO is not true, it's the case that H1 must be true, and vice versa. We also start an experiment actually assuming that the null hypothesis is the correct one, and that might be the opposite of what you were expecting. The idea is we're going to use probability and sampling techniques to see if we can get enough evidence to show that the null hypothesis is wrong as we work through the experiment. Okay, so what we're going to do is before we get heavy into mathematics and calculations, we're just going to talk about what the hypothesis test process actually looks like. There's 5 different steps to it. And the first is about how to state our null and our HO and our H1, null and alternative hypotheses. As complicated as a hypothesis test can possibly get, there's only 3 different variations and we can end up with for HO and H1. And we're going to get a chance to take a look at all 3 and see what they look like. For step 2, finding the critical values, that's a new term for us, but it's going to turn out we have worked with the concept before in the past in previous chapters. Step 3 is where our formula comes in. We're going to end up using our central limit theorem formula. And step 4 is a decision rule. It's something that we're going to use to analyze what's happened in steps 1, 2, and 3 and ultimately decide, are we accepting or rejecting the null hypothesis? And the last and final step is a summary that just qualitatively assembles together the conclusion we've made from our numbers. Okay, so let's go ahead and let's pay a little bit more attention to the 3 variations that we can end up with when we work with the null and the alternative hypothesis. Take a minute to pause the video and read through the situation here. Okay, so in the situation, it looks like we have a casino. And the casino is making about $20,000 a night. And there is a casino manager, and that casino manager thinks they found a way to rearrange the floor of the casino and get more slot machines in there. And the idea is if they can squeeze in more slot machines, the casino should be making more money and the average revenue should go up. When we're thinking about how the HO and the H1 should be written, think of the HO as the devil's advocate hypothesis. It's going to say, go ahead and try to rearrange the layout of the casino floor as much as you want. You're not going to be able to do anything. The average revenue is going to be the same thing it's always been. So we're going to go ahead and we're going to write in the null hypothesis is equal to $20,000. When it comes to the alternative hypothesis, the key inside of the question is that we're expecting an increase. That means the revenue, if this manager is correct, should go higher. But we're going to go ahead and we're going to write that as saying for our H1, the mu should be greater than $20,000. And anytime we see phrasing in the question, like increase, higher, more, larger, longer, we're going to give that a very special name. And we're going to call it a right tail test. We're going to find out in a few minutes more why we're calling it a right tail test, but it has to do with how we're going to be looking at bell curves to analyze our hypothesis test. Let's take a look at situation number 2. So take a few minutes to read through if you need, pause the video. Okay, so it looks like at Heathrow Airport, what's happening is it takes an aircraft about 18 minutes to taxi into position and take off. And this agency, IATA, they have found a way to rearrange the airport systems so that they can decrease the time it takes for a plane to taxi and take off. And if they're correct, that's a really good thing because it means they can take off and land more planes in one day and they can get more utilization out of the airport. So let's think about what we would say for our HO and our H1. Again, the null hypothesis is going to be that devil's advocate hypothesis. It's going to say, try to rearrange the grid all you want. You won't be able to change the taxi time. The taxi time is going to stand the same as it's always been at 18 minutes. When it comes time for our alternative hypothesis, we know we're expecting a decrease if this new system works, a decrease in taxi time. So we're going to go ahead and say that our mu should be less than 18 minutes if this thing works. And anytime we see words anonymous with decreasing, lower, shorter, fewer, or smaller, we're going to call that a left tail test. Let's go ahead and take a look at situation 3. Pause the video if you need to for a couple minutes. Okay, so it looks like in this case, somebody's gone and they've invented a new circuit board for a computer. And they're trying to figure out what's going to happen when they turn this thing on and make it work. Is it going to take longer or shorter amount of time for the computer to boot up? For our HO, we're just going to follow the pattern that we've been seeing. We're going to take our average and just set the mu equal to that population average. H1 is going to be a little bit more tricky this time because we're told to test for an increase and an increase or a decrease at the exact same time. So how do we do a right tail and a left tail test simultaneously? The answer is we're going to write down that we think the population average is no longer 49 seconds. We don't really know if the boot time is going to go up or down, so the best thing that we can do is state that we think it's simply not equal to the original 49 seconds. And this is what we're going to call a two-tail test. Two-tail tests can also be some of the most challenging. So keywords, how do you spot that it's time to do a two-tail test? Usually in questions, they're going to ask you to test for a difference. And that's how we can know it's time for a two-tail test. Okay, so back to our hypothesis step process. What we're going to do is we're going to take on a couple different questions, and we're going to practice just stating the null hypothesis and the alternative hypothesis, and then the critical values. Steps 3 and 4 and 5, we'll get to that part of the hypothesis testing process in a later video.